August 7, 1942, marked a pivotal moment when a contingent of 16,000 United States Marines found themselves navigating the treacherous, chest-deep ocean swells, making landfall on an unfamiliar island whose very name, Guadalcanal, proved a linguistic challenge for many. This particular landmass, a sweltering expanse of dense jungle nestled within the Solomon Islands archipelago, presented the troops with a mission that, on paper, appeared deceptively straightforward: to seize control of an airfield currently under construction by Japanese forces. With remarkable swiftness and encountering surprisingly minimal resistance, the Marines successfully secured the objective within approximately 36 hours. The Japanese contingent, in turn, retreated into the verdant depths of the jungle. A superficial assessment might have declared the mission accomplished. Yet this initial triumph merely heralded the commencement of a far more profound and harrowing ordeal. The airfield they had so swiftly captured was far from a finished facility. It was, in essence, little more than a crudely cleared strip of earth. This was no ordinary terrain, however, but tropical soil that oscillated dramatically between periods of intense desiccation under the equatorial sun and relentless inundation from torrential monsoon rains. In its parched state, the ground possessed an unyielding hardness akin to concrete, while a downpour transformed it into a viscous, chocolate pudding-like consistency. As the Marines surveyed this rudimentary landing strip, a grim realization dawned upon them. They were confronted with an existential problem, one that threatened the very survival of their entire force. For a critical truth about island warfare in the Pacific often eluded common understanding: victory was not secured merely by occupying territory, but by asserting dominion over the airspace above it. And without a fully functional runway, establishing such aerial supremacy was an unattainable ambition. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. The Japanese command was acutely aware of the strategic asset they had forfeited. Within a matter of days following its capture, their bomber squadrons initiated a relentless assault on the newly christened Henderson Field, named in solemn tribute to a pilot who had fallen during the Battle of Midway. Yet, the most formidable adversary was not the explosive ordnance raining down from above, but the insidious mud beneath their feet. Every significant rainstorm rendered the runway completely inoperable. Aircraft like the Wildcats and Dauntless dive bombers, which constituted the Marines' sole aerial protection, began to sink precariously into the saturated ground. Ground mechanics watched in dismay and horror as the landing gear struts of these vital machines vanished into the thick, clinging muck. A particularly vivid incident involved a pilot attempting to launch an intercept mission, whose aircraft's wheels carved trenches 4 feet deep before the plane even managed to achieve forward momentum, preventing him from ever becoming airborne. Consequently, the Japanese bombers he was tasked with intercepting arrived unmolested a mere 20 minutes later, underscoring the critical vulnerability. Engineers on the ground exhausted every known method in their desperate attempts to stabilize the runway. They initially tried compacting the surface with crushed coral gathered from the nearby beaches, only to witness it completely erode and wash away with the very next torrential downpour. They then resorted to laying down pierced steel planking, or PSP, material typically repurposed from bridge building supplies. However, under the relentless tropical heat, these steel plates warped and buckled, creating hazardous undulations. Further attempts involved employing heavy rollers to compact the soil, but these machines themselves frequently became mired and immobilized in the intractable mud. By the middle of August, Henderson Field's operational capacity had dwindled to an alarming 3 days out of 7. On the days it was unusable, the Marines on the ground found themselves utterly exposed and vulnerable. The absence of air cover meant that Japanese naval vessels could shell their positions with impunity, and enemy troops could be reinforced under the cloak of darkness without fear of aerial interdiction. The strategic calculus was stark and unforgiving. Without a dependable, all-weather runway, Guadalcanal was destined to fall. Should Guadalcanal be lost, the entire Pacific offensive would grind to a halt, potentially for another year, or even longer, with catastrophic implications for the war effort. Back in Washington, the gravity of this persistent problem eventually landed squarely on the desk of the Army Corps of Engineers. They were receiving increasingly desperate radio dispatches from the Pacific, all conveying the same urgent plea. We need a solution, and we needed it yesterday. The Corps of Engineers, however, was not starting from a blank slate. They had been grappling with the challenge of constructing runways on soft ground since before the attack on Pearl Harbor, conducting extensive tests at airfields spanning from the swampy terrains of Louisiana to the frozen tundra of Alaska. Yet, every method they had attempted had ultimately proven inadequate in one form or another. Now, they were witnessing the real-time, devastating consequences of these past failures unfolding 7,000 miles away in the crucible of the Pacific theater. The first earnest endeavor to address this issue materialized in early 1941, when engineers experimented with a material known as square mesh track. This innovative design consisted of a grid of welded steel bars, visually resembling a reinforced chain-link fence crafted from rebar. The underlying theoretical principle was sound: to establish a rigid framework capable of distributing concentrated weight across a broader surface area. They deployed this mesh at Langley Field in Virginia, then proceeded to roll a formidable B-17 bomber across it. To their dismay, the mesh buckled and folded like tinfoil under the immense 30-ton weight of the aircraft. The steel, it became evident, was simply not robust enough to withstand the localized, intense pressure exerted by landing gear. Conversely, increasing its thickness to achieve the necessary strength would render it so prohibitively heavy that a dedicated cargo ship would be required just to transport sufficient mesh for a single runway, making it impractical for wartime logistics. Following this, the Hessian-Matt experiments commenced in the spring of 1941. British engineers had previously reported some degree of success utilizing burlap fabric impregnated with asphalt as a temporary roadway material in the North African campaigns. American engineers hypothesized that if it proved effective for vehicular traffic, it might also serve for aircraft operations. They meticulously soaked thousands of yards of heavy jute fabric in heated asphalt, then carefully laid it across a soft ground section at Wright Field in Ohio, subsequently conducting landing tests with P-40 fighter planes. The initial landing proceeded without incident. However, the second landing immediately produced discernible ruts in the surface. By the 10th landing, the fabric had completely disintegrated, and fragments of asphalt-soaked burlap were causing severe jamming in the aircraft's landing gear mechanisms. The entire concept was summarily relegated to the rejection pile by June of that year. The approach involving coral and gravel initially appeared to hold greater promise, primarily because it emulated the characteristics of natural hardpan surfaces. In July 1941, engineers constructed test runways using a composite of crushed coral aggregate blended with volcanic rock, materials that were readily abundant on Pacific islands. They meticulously compacted this mixture with steamrollers until it achieved a hardness comparable to concrete. For a period of 3 weeks, this surface performed flawlessly under continuous aircraft operations. Then came the rain. Not a mere drizzle, but a quintessential tropical deluge that unleashed 6 inches of water in just 2 hours. The entire carefully graded surface rapidly transformed into a slurry. Engineers watched in dismay as the runway developed deep gullies, some profound enough to conceal a human. Worse still, once coral becomes saturated and begins to break down, its recompaction becomes an almost insurmountable task, effectively necessitating a complete reconstruction from scratch. Pure steel planking, or PSP, came closer to offering a viable solution than any of its predecessors. Originally conceived by the British for rapid road construction, these were flat steel plates, approximately 10 feet in length and 15 inches in width, featuring strategically punched holes to reduce weight and enhance traction. The U.S. military initiated testing of PSP for runway applications in August 1941 at Bolling Field. Engineers were highly impressed by the speed of its installation. A runway could essentially be shingled in a matter of days rather than weeks. However, PSP harbored a critical, fatal flaw when exposed to tropical heat. Steel naturally expands when subjected to high temperatures, and under the relentless equatorial sun, these plates would inevitably buckle and warp, creating hazardous ridges that posed a significant risk of shearing off aircraft landing gear. Pilots reported that landing on a warped PSP surface felt akin to touching down on a washboard while traveling at 80 miles per hour. By the autumn of 1941, the engineering teams found themselves rapidly depleting their innovative ideas and, more critically, their available time. December 1941 irrevocably altered the global landscape. Pearl Harbor was not merely a military catastrophe. It served as an urgent, unequivocal wake-up call that the Pacific theater would demand unprecedented solutions that had yet to be conceived. The Corps of Engineers consequently issued an urgent contract request to American steel manufacturers, specifying an immediate need for a runway surface possessing a unique combination of attributes. It had to be installable within days, capable of supporting aircraft weighing up to 50,000 pounds, equally effective in both mud and coral, and resilient enough to withstand tropical conditions without warping. Furthermore, it needed to be sufficiently lightweight for transport across vast oceans on cargo vessels already burdened with tanks and ammunition. Carnegie Illinois Steel Corporation, based in Pittsburgh, accepted the challenging contract. Their lead engineer, James Marston, meticulously reviewed all the previous failures and arrived at a crucial realization: everyone had been fundamentally misapproaching the problem. Prior efforts had focused on creating a surface that mimicked concrete or compacted earth. Marston's revolutionary insight was far simpler. Instead of battling the mud, one should endeavor to float on top of it. He began sketching a design that bore less resemblance to a traditional road surface and more to a flexible, metallic carpet. By February 1942, Marston's dedicated team had successfully produced a prototype. It was a steel plank measuring precisely 10 feet in length and 15 inches in width, yet every other aspect of its design was groundbreaking. First, its thickness, 3/16 of an inch of high-strength steel. This dimension was robust enough to resist buckling under significant load, yet sufficiently thin that each plank weighed only 66 pounds, heavy enough to require 2 men to maneuver it into position without specialized machinery. The engineers meticulously punched rows of holes across the entire surface, creating a pattern that resembled an industrial cheese grater. These perforations were not merely aesthetic. Each hole served a tripartite purpose. It reduced the plank's weight by approximately 30%, allowed water to drain through rather than accumulating on the surface, and created edges that provided crucial grip for aircraft tires. However, the true stroke of genius resided in the plank's edges. Both long sides of each plank incorporated intricately designed interlocking features that Marston's team had spent months perfecting. One edge featured a raised lip with a distinct, upward curving hooked end. The opposing edge was engineered with a corresponding channel. When two planks were laid side by side, the hook seamlessly slid into the channel and locked into place, not through bolts or welds, but purely by mechanical pressure. This connection was robust enough to allow a 50,000-pound aircraft to traverse the seam without the planks separating, yet it retained enough flexibility for the entire mat to bend and conform to uneven ground without fracturing. The short ends of each plank featured a distinct, yet equally ingenious, interlocking system. A straightforward overlapping joint where the end of one plank slid securely beneath the next. This clever design created a continuous surface along the entire length of a runway, devoid of any gaps wide enough to snag an aircraft wheel. Furthermore, this overlap meant that as weight was applied downwards, the planks actually locked tighter together rather than spreading apart, enhancing the overall stability and integrity of the runway. I am writing to you from a small town in the heart of England, where the skies are often gray, but the history is rich. The video topic, focusing on the engineering challenges of wartime, particularly the development of PSP for runways, is absolutely fascinating. It highlights how innovation, born out of desperate necessity, can dramatically alter the course of conflict and save countless lives. It's a testament to human ingenuity under pressure. The innovative Marston mat, a revolutionary solution for airfield construction, was meticulously designed to remain cohesive rather than disintegrate under immense pressure. In March of 1942, the United States Army conducted rigorous evaluations at Camp Claiborne in Louisiana, a location specifically chosen for its notoriously soft ground, which closely mimicked the challenging, muddy conditions prevalent in the Pacific Theater. Engineers meticulously deployed 1,200 square feet of these ingenious interlocking planks directly onto swampy, unprepared terrain. A fully loaded B-17 bomber was then rolled across this temporary surface. Observers noted the mat's visible flexibility, a distinct ripple as the colossal weight traversed its length, yet it steadfastly maintained its integrity. Over a period of 3 days, 50 takeoffs and landings were executed. While the mat sustained some superficial scratches, there were absolutely no structural failures. Upon lifting a section for internal inspection, it was revealed that the underlying ground had compressed by approximately 2 inches, but crucially, the interlocking system had distributed this compression uniformly, preventing any stress fractures or separations at the seams. This resounding success prompted the military to place an immediate order for an astounding 60 million square feet of the material. To truly grasp the efficacy of these mats, one must delve into the fundamental physics at play when a massive 30-ton bomber descends upon yielding ground. The core issue is not merely the total weight, but rather the intense concentration of that weight. A B-25 Mitchell bomber, when fully laden, tips the scales at around 35,000 pounds. However, this colossal mass is channeled through just 2 primary landing gear struts and a single tail wheel. Each main gear is equipped with 2 tires, meaning the entirety of that 35,000 pounds is compressed onto a contact area of roughly 4 square feet. This translates to an astonishing nearly 9,000 pounds per square foot impacting the ground with every landing. In stark contrast, soft soil can typically withstand perhaps 300 pounds per square foot before succumbing to the pressure. The mathematical disparity clearly illuminates the inherent challenge. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The Marston mat ingeniously resolved this critical problem through an unparalleled system of load distribution across multiple planes, literally numerous planks functioning as a unified, cohesive entity. When a landing gear wheel made contact with an individual plank, that plank did not bear the burden in isolation. The sophisticated interlocking hooks and channels ensured that the force was immediately disseminated to the 4 adjacent planks, 2 positioned on either side, and 1 directly in front and 1 behind. These planks, in turn, cascaded the load further to their respective neighbors. This intricate, cascading effect meant that by the time the initial 9,000 pounds per square foot reached the actual ground beneath, it had been expertly diffused across approximately 100 square feet of the mat's surface. Consequently, the underlying ground was subjected to a mere 90 pounds per square foot, a load comfortably within the bearing capacity of even the most notoriously difficult soil conditions. The inherent flexibility of this system proved to be as indispensable as its formidable strength. Traditional concrete runways, by their very nature, are rigid. While this characteristic performs admirably on solid, stable foundations, it leads to catastrophic failure when confronted with soft or unstable ground. Should a section of a concrete slab settle even marginally lower than the surrounding area, the unyielding material inevitably cracks. Once a crack appears, water ingress becomes inevitable, initiating a rapid and irreversible deterioration of the entire structure. The Marston mat, however, circumvented this vulnerability precisely because it eschewed rigidity. Each individual plank possessed the capacity for minute, independent movement, fractions of an inch, while steadfastly maintaining its crucial interlocking connection. The entire runway surface, therefore, effectively floated upon the ground, much like a colossal steel raft, gracefully conforming to any settling or shifting occurring beneath without fracturing or breaking apart. Furthermore, the strategically punched holes in each plank served a purpose far beyond mere weight reduction. These perforations created what engineers aptly termed a semi-permeable surface. In regions prone to heavy rainfall, a constant reality in the Pacific theater, water did not accumulate on the runway's surface, thereby eliminating dangerous hydroplaning hazards. Instead, it drained efficiently and directly through these precisely engineered holes. The true stroke of genius lay in their dimensions. The holes were only about 2 inches in diameter, ensuring that aircraft tires, which are considerably wider, still encountered an abundance of solid steel for optimal grip. Essentially, the tire perceived a continuous, solid surface, while water found an immediate escape route. Tests conducted at Wright Field in April of 1942 conclusively demonstrated that a Marston mat runway cleared water 6 times faster than conventional solid surfaces. The innovative interlocking edges also provided an unforeseen solution to a critical problem: bomb damage repair. When an enemy bomber inflicted a crater upon a Marston mat runway, the repair process differed significantly from patching concrete. Instead of patching, entire sections had to be replaced. However, because the planks interlocked without the need for welding or bolting, repair crews could simply unlock the damaged planks, effortlessly slide them out, and drop new ones into their place. At Henderson Field, engineers meticulously timed this procedure. A bomb crater that obliterated a 20-foot section of runway could be fully repaired and rendered operational again in under 40 minutes. This timeframe specifically excluded the task of filling the crater itself, focusing solely on replacing the mat surface. This efficiency stands in stark contrast to concrete repairs, where a similar incident could necessitate days of work and specialized equipment for pouring and curing new material. The inherent simplicity of the system also meant that training requirements were minimal. One did not require specialized engineers to install Marston mat, merely men capable of following a pattern and executing tasks swiftly. On August 17, 1942, at Henderson Field, the inaugural consignment of Marston mat arrived on Guadalcanal, transported by cargo ships that navigated a perilous gauntlet of Japanese submarines. Naval Construction Battalion personnel, famously known as CBs, disembarked a staggering 36 tons of steel planking onto the beach, all while Zero fighters relentlessly strafed the shoreline. Their monumental task was governed by a deadline measured not in days, but in mere hours, before the inevitable arrival of the next Japanese bombing raid. The CBs, most of whom had been civilian construction workers, carpenters, steelworkers, and equipment operators building highways and bridges across America just months prior, had never encountered this material before. Now, they found themselves in an active combat zone, attempting to construct a runway from scratch under enemy fire. Their initial realization was the sheer physical toll. 66 pounds per plank seemed manageable on paper, but became an arduous burden when carrying those planks hundreds of yards in 100-degree heat and 90% humidity. Out of sheer necessity, they rapidly developed an efficient rhythm. Two-man teams would retrieve planks from stockpiles and haul them to the runway's edge. A third man assumed the crucial role of guide, meticulously positioning each plank to ensure proper alignment of the interlocking edges. The first row was laid with relative ease, simply placing planks side by side on the cleared ground. However, every subsequent row demanded the precise hook and channel connection. The technique they perfected involved tilting the new plank at a slight angle, sliding its hook beneath the channel of the already positioned plank, and then dropping it flat. When properly seated, a distinct metallic click resonated, a sound that quickly became the most satisfying auditory cue these men knew. That click signified a secure lock. The construction proceeded in frenetic bursts, punctuated by enemy air raids. Japanese bombers targeted Henderson Field almost daily, sometimes twice within a single day. The CBs swiftly learned to watch for spotters. A lone reconnaissance plane signaled that bombers were likely an hour away. When the alarm sounded, everyone immediately dropped their tools and scrambled for foxholes. After the bombers had passed, dropped their ordnance, and departed, the CBs would wait a cautious 10 minutes for any unexploded ordnance to detonate. Then, they would return to the runway, resuming their work precisely where they had left off. If a bomb struck a section they had already completed, they would unlock the damaged planks and replace them. If it hit a section yet to be reached, they would fill the crater with coral and continue laying the mat directly over it. By August 20th, a mere 3 days after the initial mat shipment arrived, a section of runway 200 feet long and 75 feet wide was declared operational. While not a complete runway, Henderson Field would ultimately require 5,000 feet to safely accommodate bombers. It was sufficient for fighter aircraft. That very afternoon, 19 Wildcat fighters and 12 Dauntless dive bombers, designated VMF-23 and VMSB-232, flew in from the carrier Enterprise. These aircraft formed the famed Cactus Air Force, named after Guadalcanal's radio call sign. They were landing on a surface that had not even existed 72 hours prior. Pilots reported that landing on Marston mat felt distinctly different from concrete or compacted earth. There was a perceptible give to it, a subtle flex that could be felt through the landing gear. Some pilots likened it to landing on a firm trampoline. This inherent flexibility actually made landings more forgiving. Planes approaching too hard did not bounce as violently because the mat absorbed a portion of the impact energy. By September 5, 1942, Henderson Field boasted a complete Marston mat runway, measuring an impressive 5,200 feet long and 150 feet wide. The total installation time, despite numerous delays caused by air raids and artillery fire, was a remarkable 19 days. Traditional concrete construction methods would have demanded at least 3 months under ideal conditions, a luxury entirely absent on Guadalcanal. Guadalcanal unequivocally validated the concept, but it was the subsequent events that truly underscored the strategic value of portable runways. By early 1943, the U.S. military was meticulously planning an ambitious island-hopping campaign across the Pacific, an offensive that would eventually span 7,000 miles from the Solomon Islands to the Japanese home islands. Every single one of these islands would necessitate an operational airfield, and they would need them with unprecedented speed. The Japanese strategy hinged on transforming each island into an impregnable fortress, designed to withstand months of siege. Marston dramatically compressed this timeline. In February 1943, on the Russell Islands, the Marines landed fully anticipating fierce resistance, only to discover that the Japanese forces had evacuated. Within an astonishing 60 hours of the first troops hitting the beach, Seabees had constructed a fully operational fighter strip using Marston mat. The sheer speed of this accomplishment was so astounding that when Admiral William Halsey flew in to inspect it, he inquired of the battalion commander whether construction had commenced before the island was actually secured. They had not. They had simply achieved an unparalleled level of efficiency. The Russell Islands airfield immediately provided vital air cover for the subsequent advance up the Solomon chain, reducing what would have been weeks of vulnerability to mere days. The vulnerability of newly captured territories was dramatically reduced, often to a mere matter of days. Consider Munda Point on New Georgia Island in August 1943. This particular operation presented an extraordinary challenge, as entrenched Japanese forces remained, deeply fortified in bunkers that commanded a clear view of the proposed airfield site. Despite these perilous conditions, the Seabees proceeded to lay Marston mat, enduring direct enemy fire. They devised and executed tactics that, on paper, appeared utterly self-destructive, yet proved remarkably effective. One half of the battalion diligently installed the metal planks while the other half simultaneously engaged the adversary, providing crucial covering fire with their rifles and machine guns. The human cost was significant, with 14 brave men losing their lives and 47 others sustaining injuries. Nevertheless, the sheer determination of these engineers ensured the runway became fully operational within an astonishing 11 days. Even as Japanese snipers were still being systematically cleared from the perimeter, Marine Corsair fighters were already taking to the skies from Munda, embarking on critical combat missions. A few months later, in November 1943, the strategic focus shifted to Bougainville, an island that would become a crucible for military innovation, particularly in the realm of prefabrication. Rather than painstakingly laying individual interlocking planks, engineers stationed in Australia began to preassemble substantial sections of Marston mat into colossal panels, each measuring 50 feet by 15 feet. These gargantuan, pre-constructed segments were then meticulously loaded onto LSTs, or landing ship, tanks, and transported across the vast ocean entirely intact. Upon the LSTs making landfall at Bougainville's beaches, powerful cranes deftly hoisted these pre-assembled sections directly onto ground that had been swiftly prepared for their reception. A runway that, under traditional methods, would have consumed a fortnight for plank-by-plank installation was astonishingly completed in just 4 days. By December of that same year, Bougainville boasted 3 fully functional Marston mat runways, strategically arranged in a triangular pattern to facilitate simultaneous takeoffs and landings, irrespective of the prevailing wind direction. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The sheer volume of Marston mat production figures vividly illustrates its escalating importance and how utterly central this groundbreaking technology became to the war effort. In 1942, a consortium led by Carnegie, Illinois, alongside 9 other prominent steel manufacturers, collectively manufactured an impressive 8 million square feet of the matting. The following year, 1943, witnessed an exponential surge, with production soaring to an astounding 40 million square feet. By 1944, the annual output reached a staggering 60 million square feet, a quantity so immense that, if laid end to end, it would stretch the entire distance from New York to Philadelphia, effectively creating a continuous runway. The military's insatiable demand for Marston mat was so profound that it inadvertently triggered a significant steel shortage, impacting other vital wartime initiatives. Consequently, the production of tanks, a cornerstone of ground combat, experienced temporary reductions, as the nation's steel furnaces were strategically reprioritized to meet the urgent need for runway matting. This critical prioritization underscores the indispensable role Marston mat played in the Pacific Campaign. The narrative of the mat's versatility continues into January 1945, at Lingayen Gulf in the Philippines. During the pivotal Lingayen Gulf operation, Marston mat was deployed in an entirely novel manner, far removed from its original design intent. Resourceful engineers ingeniously utilized the perforated steel planks to bridge the soft, sandy beaches, effectively creating immediate, robust piers and essential roadways for the relentless flow of supply trucks. Through this innovative application, they quickly ascertained that the mat possessed an equal, if not superior, efficacy in distributing the substantial loads of wheeled vehicles as it did for aircraft. This transformative discovery meant that vital supply convoys, which would have inevitably become mired and bogged down in the treacherous beach sand under normal circumstances, could now drive directly and unimpeded from their landing craft straight to the inland supply dumps, drastically enhancing logistical efficiency and speed. Moving to February 1945, the grim, volcanic expanse of Iwo Jima presented perhaps the most iconic, albeit often unrecognized, installation of Marston mat during the entire conflict. The island's unique geological composition, a volcanic ash so incredibly fine and unconsolidated that attempting to build upon it felt akin to constructing on powdered sugar, rendered conventional construction methods utterly unfeasible. Concrete simply would not cure properly, as the ubiquitous ash inextricably permeated the mixture, compromising its integrity. Similarly, the concept of compacted earth was a non-starter, as there was no actual earth, only this pervasive, powdery ash. In this seemingly insurmountable environment, Marston mat emerged as the singular viable option. With incredible resolve, CBs meticulously laid these critical planks across all 3 airfields on the island, often under the most intense combat conditions, even as the ferocious battle for Mount Suribachi continued to rage with undiminished ferocity. With the cessation of hostilities in August 1945, military strategists and planners largely anticipated that Marston mat would swiftly become obsolete within a matter of months. The prevailing assumption was that the advent of peacetime would afford ample opportunity to construct permanent, robust concrete runways, negating the need for temporary solutions. Consequently, vast quantities of the steel matting were stockpiled at various depots scattered across the Pacific, with thousands of tons languishing in warehouses, awaiting their eventual fate of being scrapped or disposed of through sale. However, history had an unexpected twist in store. On June 25, 1950, when North Korea launched its invasion of South Korea, the U.S. military found itself in a frantic scramble to establish crucial air superiority in a theater almost entirely devoid of existing infrastructure. In this moment of urgent need, those supposedly forgotten stockpiles of Marston mat were abruptly retrieved from their long-term storage. The topographical and climatic characteristics of Korea diverged dramatically from the tropical islands of the Pacific. It was a land of rugged mountains, subjected to brutal winters, where the very soil froze solid to considerable depths. Engineers initially harbored doubts, questioning whether a mat designed for the humid jungles of the tropics could possibly function effectively in sub-zero temperatures. Their concerns were quickly addressed by practical experience. While steel indeed becomes more brittle in extreme cold, the ingenious interlocking design of the mat proved robust enough to maintain its structural integrity. Furthermore, the inherent flexibility that had enabled the mat to perform so admirably on soft, yielding ground now demonstrated its utility on rigid, frozen terrain. When the soil froze and subsequently expanded, the mat gracefully flexed upwards, accommodating the changes. Conversely, as the ground thawed and contracted, the mat seamlessly settled back into place, exhibiting neither cracking nor separation, a testament to its remarkable adaptability. Kimpo Airfield, situated near Seoul, quickly became the definitive test case for this resilient technology. By September 1950, the airfield lay in utter ruins, its concrete runways systematically destroyed by retreating North Korean forces. Yet, with astonishing speed and ingenuity, U.S. Air Force engineers deployed Marston mat directly over the shattered concrete debris, miraculously creating an operational runway in an incredible 72 hours. Within days, F-86 Sabres were already launching combat missions from Kimpo, even as concrete repair crews were still laboriously jackhammering rubble on adjacent sections of the airfield. The Korean War ultimately saw Marston mat utilized at 38 different airfields, and during this conflict, the military began to adopt a new designation, PSP, or Pier Steel Planking. While the familiar name Marston mat gradually receded from official parlance, the underlying technology remained fundamentally identical and equally effective. Years later, in 1965, the durable mat reappeared on the global stage, this time in Vietnam, remarkably still functional despite being almost 25 years old. Astonishingly, some of the very same steel planks that had been laid on Guadalcanal 2 decades prior were once again pressed into service, demonstrating an incredible longevity. Engineers deployed these enduring sections at crucial locations such as Da Nang and Bien Hoa, where they were instrumental in creating vital dispersal pads for helicopters and expanding existing runways to accommodate increased air traffic. The Vietnamese climate, characterized by intense monsoons, oppressive heat, and acidic soil, bore an almost uncanny resemblance to the Pacific Islands for which the mat was originally engineered. Consequently, it performed with the exact same reliability and effectiveness as it had back in 1942, proving its timeless utility. However, the narrative of Marston mat takes an utterly unexpected turn following the Vietnam War. Post-conflict, this resilient material began to transition into an array of civilian applications. Oil companies, recognizing its unique properties, adopted it for use in the challenging Arctic environments of Alaska and Canada. Here, it was employed to construct temporary roads and drilling pads across the delicate permafrost, crucially achieving this without causing irreparable damage to the fragile tundra ecosystem. The very same principles of weight distribution that had prevented heavy bombers from sinking into the soft mud of the Pacific now served to prevent massive trucks from melting the underlying permafrost. Notably, even environmental groups lent their support to its use, appreciating its removability. Once drilling operations concluded, the mat could be lifted, allowing the tundra to recover, a stark contrast to the permanent scarring left by traditional gravel roads. In January 2010, the devastating magnitude 7.0 earthquake that struck Port-au-Prince, Haiti, presented a new, urgent challenge for the venerable Matt. While the international airport's primary runway remained miraculously intact, the surrounding essential infrastructure was utterly annihilated, creating immense logistical bottlenecks for desperately needed relief flights. In response, the U.S. military swiftly airlifted pallets of Marston mat, which, remarkably, continues to be manufactured, and deployed it across the damaged taxiways and parking aprons. This immediate intervention enabled cargo planes, laden with critical medical supplies and food, to unload and taxi to newly established parking areas that had literally not existed just 48 hours earlier. In a poignant full circle, the technology originally conceived and designed to wage war against the Japanese Empire was now actively engaged in saving the lives of earthquake victims, showcasing its profound humanitarian adaptability. Today, modern military forces around the globe steadfastly maintain extensive stockpiles of this enduring technology. The U.S. Air Force, for instance, now refers to it as AM2 matting, an acronym standing for Aluminum Membrane Version 2, reflecting a strategic shift from steel to lighter aluminum alloys to reduce overall weight. Yet, despite this material evolution, the fundamental design remains instantly recognizable. The same ingenious interlocking edges, the familiar perforated surface, and the identical basic concept that Marston first sketched out in 1942. Its utility extends far beyond American forces. The British Royal Air Force employs it, and NATO forces deployed it in Afghanistan to expand crucial parking areas at Bagram Airfield. It consistently appears in the aftermath of natural disasters, typhoons, floods, and hurricanes, wherever there is an urgent need for instantaneous infrastructure on damaged or unprepared ground. Furthermore, the original Marston mats themselves are still very much in evidence. Sections of these historic planks can be found repurposed in various civilian roles, serving as sturdy walkways, durable bridge decking, and even unique decorative fencing. On some remote Pacific islands, operational sections laid during World War II astonishingly remain in place, now weathered and worn by decades of exposure, but still remarkably functional after 80 years. While history books and documentaries often celebrate the decisive victories achieved by tanks, planes, and ships, the profound reality is that wars are frequently won by the unsung, unseen infrastructure, the often unsexy logistics, the intricate supply chains, and, crucially, the ability to transform a seemingly worthless piece of ground into a fully functional military asset with a speed that utterly defies enemy expectations. Marston mat fundamentally reshaped the entire equation of how the Pacific War could be waged. Yet, remarkably, the vast majority of people remain entirely unaware of its existence or its pivotal role. Prior to the advent of these ingenious steel planks, the act of capturing an island necessitated a commitment to months of arduous construction before that island could yield any strategic utility. Forces would seize the ground, often at immense cost, only to then endure a protracted waiting period, while engineers meticulously surveyed the terrain, graded the earth, poured concrete, and patiently awaited its full curing. Throughout this extended interval, the newly captured forces remained dangerously vulnerable, and the island itself was, in essence, nothing more than expensive, strategically inert real estate. The Japanese High Command comprehended this strategic calculus with chilling precision. Their defensive doctrine was meticulously predicated on the assumption that each captured island would consume such an inordinate amount of time to become operational that the relentless American momentum would inevitably stall and dissipate. Their strategy involved digging in deeply, forcing the invaders to pay a steep price in blood for every inch of territory, knowing that even after a victory, the Americans would be bogged down for months, striving to render the island functional. The very concept of island hopping was, by design, intended to be a slow, grinding progression. Marston Matt, however, utterly shattered this deeply ingrained assumption. Suddenly, American forces could land on an island and have operational aircraft launching from its newly established runways within a single week, and in some extraordinary instances, within mere days. This revolutionary capability irrevocably altered the very nature and potential aggression of the American advance across the Pacific. Consequently, islands that had previously been deemed strategic liabilities due to the anticipated, prohibitively long development timelines were instantly transformed into viable, attractive targets. The success of the Central Pacific Campaign, encompassing pivotal engagements such as Tarawa, Kwajalein, and Saipan, was intrinsically linked to this newfound capability. Captured islands could now immediately serve as forward bases, directly supporting the subsequent assault, rather than becoming costly and momentum-sapping pauses in the relentless drive towards victory. The statistical evidence is stark and irrefutable. By the close of 1944, the U.S. military had engineered and constructed over 300 airfields across the vast expanse of the Pacific theater. A staggering proportion, approximately 220 of these critical airfields, utilized Marston Matt, either partially or entirely, for their construction. Without the transformative impact of this technology, it is estimated that perhaps only a third of those airfields would have been built, and, crucially, their construction would have consumed 3 times as long. Such a shortfall would have translated directly into fewer forward bases, necessitating significantly longer flight distances for vital bomber missions, and critically, a reduced air coverage for naval operations. The entire timeline of the Pacific War, a conflict of unprecedented scale and complexity, would have potentially been shifted by months, perhaps even a full year, underscoring the profound and often overlooked strategic significance of this humble, perforated steel planking. One might consider, for instance, the extensive aerial bombardment campaign directed against Japan itself. The formidable B-29 Superfortress aircraft, whose relentless sorties ultimately compelled Japan's capitulation, originated predominantly from the Marianas Archipelago, specifically the islands of Saipan, Tinian, and Guam. These strategically vital landmasses were wrested from enemy control during the summer of 1944. Remarkably, by November of that same year, a mere 5 months subsequent to their capture, these very islands were already serving as launch pads for extensive aerial bombardments aimed at Tokyo. This extraordinary swiftness was solely attributable to the fact that military engineers possessed the capability to rapidly deploy Marston Matt runways, robust enough to accommodate the most formidable heavy bomber in the United States aerial fleet, all within a mere span of weeks. Conventional methods involving concrete pavement construction would have inevitably protracted the initiation of these critical raids until mid-1945, at the earliest, a delay that would have fundamentally altered the strategic computations for the conflict's conclusion, potentially prolonging the war and exacting an even greater toll in human lives and resources. Beyond this specific operational triumph lies a profound overarching insight concerning ingenious problem-solving amidst intense duress. The Carnegie Illinois Company, instrumental in this innovation, did not, in fact, conceive of some previously unknown substance or a groundbreaking industrial methodology. Instead, their approach involved a meticulous examination of established methodologies for steel production and shaping, from which they then posed more incisive and fundamental inquiries. Their design challenges revolved around critical paradoxes. How could one imbue material with immense strength without simultaneously rendering it inflexible? How could lightness be achieved without compromising structural integrity and leading to inherent weakness? Furthermore, how could a complex engineering solution be simplified sufficiently for fatigued personnel operating within active combat zones to assemble it correctly and efficiently? The true sophistication resided in its straightforward design: panels that interlock seamlessly, perforations meticulously designed for efficient water runoff, and a type of steel specifically engineered to yield under stress without fracturing. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment below about where you are from and what you think about the video topic. Analysts of military campaigns frequently characterize the Pacific War as primarily a conflict dominated by aircraft carriers, a relentless submarine campaign, or fundamentally a war of logistics. While these assertions hold undeniable veracity, beneath their surface lies a deeper truth. It was also a conflict fundamentally defined by critical engineering challenges surmounted against seemingly insurmountable temporal constraints. Indeed, Marston and his dedicated team at Carnegie, Illinois potentially preserved a greater multitude of human lives and accelerated the conflict's resolution more profoundly than any solitary implement of warfare, achieving this not by means of devastation, but through the remarkable power of creation. They ingeniously devised methods to transform treacherous mud into functional runways, dense jungles into operational air bases, and hitherto insignificant landmasses into pivotal offensive staging grounds. In essence, they rendered that which was deemed logistically unattainable into a tangible reality. And in the crucible of war, the mastery of supply chain and operational movement constitutes the paramount determinant of success. Those perforated steel planks, with their deceptively simple interlocking edges, did not merely serve as the foundation for airstrips.